Okay, we're going to do every exam question that's ever been asked on standard form. This includes all the exams from 2017 to 2021. Now, if you want this document to use it for yourself, it is fully hyperlinked. It is going to be linked in the description, so go and check that out, as well as the rest of the things on my channel. And if you do like this at the end of it, it'd be great if you could drop it a like and keep subscribed to me. Okay, so we're going to look at standard form, and there are these four kinds of questions that we've got. We've got writing, ordering, and comparing, multiplying and dividing, mixed calculations, and substitution. So we're just going to get started straight away. Notice this is a calculator one, so we can use a calculator if we have to, but these are pretty straightforward. Now we're going to write this in standard form. Remember, the first number is going to have to be in between the 9 and 10. Sorry, in between 1 and 10. So we're going to do it as our 5.62. And actually, there's a bit of a shortcut here. Because it's the small numbers, you can actually just count how many zeros there are, and it is times 10 to the power of minus 3. Now, you can't do that with big numbers. 1.452 is an ordinary, times 10 to the 3 is an ordinary number. Timesing it by 10 to the 3 means timesing it by 1,000. So it's just 1,452. Pretty straightforward for those ones. Like I said, I'm not normally going to be teaching standard form. It's more just going through the questions. So if you want to know how to do standard form, I've got a full playlist of this on my channel homepage. So we've got the correct answers of these two here and here. Okay, so we're going to start off writing this one in standard form. Now, the beginning number is going to be 3.246, and that decimal point has got to move 1, 2, 3, 4, 5, 6, 7, including those zeros. So it is times 10 to the power of 7. Writing this one as an ordinary number, remember I said when it's with the negative powers or small numbers, it actually just tells you how many zeros there are. So it's 0.00496. And then Asma was asked to compare the following two numbers. We've got 6.212 times 10 to the 8, and that B is 4.73 times 10 to the 9. She says that 6.212 is bigger than 4.73, so A is bigger than B. Is she correct? You must give a reason for your answer. Well, she thinks this is bigger than this. Well, no, she isn't correct because of the 10 to the 9. 10 to the 9 is bigger than 10 to the 8, so B is larger. So is she correct? No, B is larger because 10 to the power of 9 is higher or more than, is bigger than 10 to the power of 8. So with standard form, it's about the second number that's important, not the first number. So we've got this, and no with an explanation. You can see some things. 10 to the 8 is smaller than 10 to the 9, or we said it the other way around to that, so that's perfectly fine. Okay, let's have a look at this one that we've got. We want to try and put these numbers in orders of size, and we're going to start with the smallest number. Now, we want to be able to put them into standard form. This one is already in standard form, but the second one needs changing. So I'm going to divide this first one, so it's 6.72, but because I divided this number by 10, I need to times this number by 10, which means I'm adding 1 on to the power, so that's going to be 10 to the power of minus 3. This number I'm going to divide by 100, so I need to times this number by 100, which is timesing it by 10 squared, so that is 10 to the power of 6. And this last one, we can do the shortcut for the small numbers, that's going to be 6.72. There are 4 zeros, so the shortcut is it's 10 to the power of minus 4. Now all we need to do is just compare the powers, so we've got a 5, a minus 3, a 6, and a minus 4, and we're going to start with the smallest number, so the smallest of those is the one that's the power of minus 4. So I'm going to begin by writing that number that's at the end, which is 0.000672. Now the next smallest is this one here, where it's the power of minus 3. But I'm going to write it as its original number, like this. And then between those last two, we can see that's a power of 5, and then the last one is a power of 6. So it's going to be 6.72 times 10 to the power of 5. And then our last one is 672 times 10 to the power of 4. Now, sometimes people say, oh, what happens if I wrote these ones down instead? Then it's perfectly fine. You don't have to have it written in the original printed ones. You could do it with their equivalent forms as well. I'm just going to change that 0 so it looks a little bit neater than what I'd got written. So we'll double check we've got these in the right order. Yep, we do. They're over here. So it's minus 4, 5, and 4. Yeah, we got those in the right order. So I'm pretty happy with that one. Okay, this is another non-calculator one. We're going to do it as an ordinary number. Remember that power of minus 6? It just means there's going to be 6 zeros. 1, 2, 3, 4, 5, 6, 7, 9, 7, because it's dividing by 10 6 times there. Now we're going to work out the value of this calculation, and it's a division one. So I usually like to write these ones like a fraction. It just helps me to spot what's going to go on here. So I'm going to be doing two separate parts. I'm actually going to do the 2.52 divided by 4. That's one of the things I'm going to do. And then the other thing is the 10 to the power of 5 divided by 10 to the power of minus 3. Let's start off by working on this one. So I'm going to see how many times does 4 go into 2.52. Well, 4 doesn't go into 2, so I'll carry it across. 4 goes into 25, 6 times, remainder 1, and 4 goes into 12, 3 times. So we get 0.63 for the beginning part of the number. Now this part that we've got, let's just try and write this so I've got a bit more space next to it. We subtract the powers. So we're going to do 5 subtract negative 3. And when you do 5 subtract negative 3, that's actually 5 plus 3. So it's going to be 10 to the power of 8. So it's 0.63 times 10 to the power of 8. However, it wants the answer in standard form, and this number that we've got here is not in standard form. So we need to do a bit of work on that. What I'm going to do, I'm actually going to move this down here so I have even more space. I'm going to change the 0.63. I'm going to multiply it by 10 to get 6.3. But because I multiplied that one by 10, I need to divide that one by 10 so that it goes from 10 to the power of 8 to 10 to the power of 7. So I'm just going to write down here, I times that by 10, and so I have divided that by 10. Okay? Let's just tidy up that power of 5 so it looks a little bit neater. Okay, so here is the answer. Let's double check we've got this one right. So we've got 6.3 times 10 to the 7 and the 0.0000 with the 6 zeros, 797. Okay, we are now on a calculator one. So this is really just how you use your calculator. Now, my calculator that I've got at the bottom has this EXP button. It says EXP, but lots of your calculators will have this 10 times 10 to the power of. This literally just means you can use that button to type it in. So if I'm going to do 13.8 times 10 to the 7, you can put brackets if you want to, but I'm just going to write 13.8. When I do it, mine comes up with an E. That just means times 10 to the 7. And I don't need brackets, but you can put them in if you want to, times 5.4 times 10 to the power of minus 12. And we come up with the answer of 0.0007452. It wants it as an ordinary number, so I can just leave it as it is because it's already as an ordinary number. So pretty easy there. It's just about how you type it in the calculator. Same thing for this. We're going to do this straight into the calculator. So I'm going to do 3.42 EXP minus 7. And I'm going to do that divided by 7.5, EXP. Let's go back here to the calculation. Let's clear it. So we're going to do 3.42 EXP minus 7 divided by 7.5 EXP minus 6. And we get the answer 0.0456, but we want that in standard form. So to put that in standard form, we know it's going to be a 4.56. And remember, with small numbers, you can do the shortcut and just count the zeros. So it's going to be a negative 2. So it's 4.56 times 10 to the power of negative 2, which is the answer we have. We've got another one from a calculator paper here. So we've got a table about information of 8 planets. And it wants us to write down the name of the planet with the greatest mass. So here is the mass column that we've got. We're literally just looking for the one that has got the highest power. And I think the one with the highest power is this one. So we can say that the planet with the greatest mass is Jupiter. Find the difference between the mass of Venus and the mass of Mercury. Well, difference means to do subtract, and it's a calculator paper. So I'm going to take the mass of Venus, which is 4.869 times 10 to the power of 24, and the mass of Mercury is 3.302 times 10 to the power of 23. So I'm just going to type that into the calculator, again using that times 10 to the power of button or this E button, depending on what you've got on your calculator. 4.869 times 10 to the power of 24 minus 3.302 times 10 to the power of 23. And when we subtract it, it's written as this very, very, very long number that we've got here with loads and loads of zeros. Now, there is a way of getting this put into the calculator, but actually I think we can probably spot that it's still got 24 zeros in it. So we've got from the end 3, 6, 9, 12, 15, 18, 21, 24. Sorry, not 24 zeros, but 24 numbers after the 4. So it is 4.5388 times 10 to the power of 24. It doesn't say to give it in standard form, but I think it's going to be best to give that one in standard form. Nishat says that Neptune is over 100 times further away from Earth than Venus is. So we're going to look at the distance from Earth, we're going to look at Neptune, and we're going to look at Venus. Now this time it's not going to be subtract, it's saying how many times further away it is, so it's going to be a division. So I'm going to do 4.35 times 10 to the 9, that's for Neptune, and we're going to divide that by Venus, which is 4.14 times 10 to the 7, and we'll just see what that comes up with when we calculate this. So I'll put it in as a fraction, 4.35 times 10 to the 9 divided by 4.14 times 10 to the 7, and we get the answer 105.07 something, which is more than 100 times. So yes, Nishat is right, because it's more than 100. So let's double check these. We got Jupiter, we got 4.5388 times 10 to the 24, and we got yes, with it being supported. Okay, we've got another calculator paper. We're going to write this in standard form. It's going to be 8.623, and there is 1, 2, 3, 4, 5 zeros. So we can do that shortcut of 10 to the power of minus 5. This is just going to go straight into the calculator. So I'm going to do a fraction, 3.2 times 10 to the 3, times 5.1 times 10 to the minus 2. And on the bottom, it is 4.3 times 10 to the minus 4. Now, it wants it in standard form to 3 significant figures. So I'm going to start off writing it to 3 significant figures. Well, it's 3, 7, 9, 5, 3, 4. Let's just now do this to 3 significant figures. After the third significant figure is a 5, so it's going to be 380,000. Now, to get that in standard form, that is going to be 3.8, and the decimal point would have to move 1, 2, 3, 4, 5 spaces. So 3.8 times 10 to the 5 for that one. So the calculator can really help you. Oh, I've done something completely wrong. Have I not typed this into the calculator correctly? So we've got 3.2 times 10 to the 3. Oh, I did times. I hope you spotted that when I was doing this. I'm going to delete that and change that to an add. Very easy to kind of make these mistakes here. Now when I press equals, it changes the answer completely. So let's just quickly erase this. It is 7,441,979. Now let's round that to 3 significant figures. After 3 significant figures, that is going to be 7,440,000. Now to get that into standard form, that is going to be 7.44, and that is going to be times 10 to the power of 6, because it's having to move those 6 spaces that we've got there. So very easy to make a mistake, but I quickly corrected that, seeing I'd got that wrong. Okay, we've got some more calculations. It says in May 2019, the distance between Earth and Mars was 3.9 times 10 to the 7. A signal was sent from Earth to Mars. Assuming that the signal was travelling at a speed of 3 times 10 to the 5 kilometres per second, how long does it take? So we're looking for the time, and we know that time is the distance divided by the speed. So the distance that is between them is 3.9 times 10 to the 7. And the speed it's travelling at is 3 times 10 to the 5. So we can just go straight in with the calculator to do this. So I'm going to do 3.9 times 10 to the power of 7. I could either do it as a fraction or just as a division, and 3 times 10 to the 5. And we get that it is 130, and the units for this are seconds. So it is 130 seconds. The speed of the signal sent from Earth to Mars in May 2019 was actually less than this. How does this affect your answer? Well, this is now saying that the speed is slower. So if the speed is slower, it's going to take longer. The time will be longer. It's just kind of logic, right? If something is going slower, it will take longer. So we've got 130 seconds and the time will be longer. Great. Okay, we've got another calculator one. A person's heart will beat approximately 10 to the 5 times each day. A person lives for approximately 81 years. Work out an estimate for the number of times a person's heart beats in their lifetime. Give your answer in standard form, correct to 2 significant figures. Now, because it's an estimate, you actually are allowed to do some rounding here. But I think the reason they're saying it's an estimate is because of these approximate things. So let's try and find out how many times that they are going to have their heart beat. So we're going to say it's 10 to the 5 each times of a day. So that's for one day. For a year, it would be 365, and for 81 years, it would be 81. So we're going to try and calculate this. Now we could, if you wanted to, you could round it and you could do 10 to the 5 you could times it by 400, and you could times it by 80, and they would also accept that as well. But let's see how it works out with this one. So we're going to do our 10 to the power of 5. We're going to multiply it by 365 and then by 81. And we get let's do this in standard form straight away. It's actually going to be to two significant figures. It's going to be 3.0 times by 10 to the power of 9. So there's an estimate that we've got there. For part B, it says 2 times 10 to the power of 12 red blood cells have a total mass of 90 grams. Work out the mass of one red blood cell. So if we're saying that we want to find out what one red blood cell is, we're going to have to do 90 divided by how many we've got, which is times 10 to the power, 2 times 10 to the power of 12. So this time it's a division, and I'm going to do 90. You could do it just as a fraction or using the division button. I'm going to do it as a fraction though today, so I'll do 90 divided by 2 times 10 to the power of 12, and my calculator gives it in standard form straight away, which is 4.5 times 10 to the power of minus 12 grams. Let's double check we've got these right. So we've got 3.0 times 10 to the 9 and 4.5 times 10 to the minus 11. What did I have wrong then? Oh, did I type it in right? No, again, I didn't type it in correctly. I hope that you're watching this and thinking all these things are going wrong. So it's actually 45. My calculator comes up as 45 times 10 to the 12. So we're going to need to adjust this. Because it's not in standard form, I'm going to need to divide that by 10 and times this by 10, which means increase the power by 1. So I've made 2 mistakes in this video. I don't normally make that many mistakes, but oh well. Now you'll see in this beginning part here, you could have done some rounding as well, because they may have accepted the values with rounding. Okay, we're going to do this as an ordinary number, nice and easy. So it's going to be the 0.5 is going to be 5 spaces, so it goes over the 5 with 1, 2, 3, 4, 5. So the decimal point was here, 1, 2, 3, 4, 5. So it's 450,000. Writing 0.007 in standard form, well, that is 7 times 10 to the power of minus 3, that shortcut of those 3 zeros. It's a calculator paper, so we're going to go straight in, and we're going to do 4.2 times 10 to the 3 plus 5.3 times 10 to the 2. We get the answer 4,730, so I'm going to put that in standard form. That is 4.73 times 10 to the power of 3, because that decimal point moves 3 spaces. So we've got those 3 correct answers there. This time we're going to do some substitution. So it just wants you to work out the value of t, giving your answer to 3 significant figures. Now again, it's just typing in on a calculator, so it's going to be the square root of 5.6 times 10 to the power of minus 5 divided by 1.4 times 10 to the power of minus 4 cubed. So I'm just going to type this using my exponential button. So I'm going to first of all press the square root button, then the fraction button, and now I'm going to type in the numerator 5.6 times 10 to the power of minus 5. I'm going to put some brackets here so that I can do the cubing. I'm going to do 1.4 times 10 to the power of minus 4. I'm going to close those brackets, and then I'm going to cube that bit that we have. And it wants our answer to be in standard form to 3 significant figures. So I'm just going to write this number here down to 3 significant figures. I'm going to, first of all, just write it down as like a whole number like this. That's to the nearest number. So now I'm going to do it to 3 significant figures. That's going to be 4520. So to get that in standard form, that is 4.52 times 10 to the power of 3. Now it says that W is increased by 10%, D is increased by 5%. Lottie says the value of T will increase because both W and D are increased. Lottie is wrong. Explain why. We have to be careful. When you increase something in the denominator, you actually make the number smaller. So let's just actually see what happens here. Let's actually do the calculation. You could do it using reasoning, but you could actually just work out with the calculations. So we're now going to say what T would be. It would be the 5.6 times 10 to the power of minus 5. If that's increasing by 10%, that is multiplying by 1.1. And then we're going to do D increased by 5%. So that's 1.4 times 10 to the power of minus 4. We're going to increase it by 5%, timesing it by 1.05, and it is still being cubed. So I think this is probably the easiest way to do this one, is actually to just kind of do the calculation again. So I'm going to go back through my calculation. I'm also now going to multiply by 1.05, and if I go to the numerator, I'm going to multiply by 1.1. And when I multiply this by 1.1, I get 4,404. Oh, I didn't mean to press that twice. 4,404. 4,404. And I've rounded that to just the nearest whole number. And to three significant figures, that's 4,400. Lottie is wrong. So the reason it is wrong, she is wrong, as t is now 4,400, not 4,520. So it's gone lower. And you can see that we've got that calculation for the 4.40 over here, and we got this correct answer for the beginning part of the 4.52 times 10 to the 3. So that's all of the questions that have been asked on standard form. If you are finding these useful, do make sure you're subscribed, and I'm about to just start going through all of the ones on algebra.